In this lecture, I will continue the discussion of the density matrix. In the previous lecture, I started to discuss about I started to reconsider the third postulate, which was related to measurement, and then I introduced a few a little bit different types of measurement definition, and then we also our discussion also led to the discussion of POVM. And at the end of the last lecture, I also started to reconsider the second postulate. And then the issue with the second postulate is in the definition of the second postulate, it actually requires that the evolution of the quantum state can be described by a unitary transform only if it is closed quantum system. So what is the meaning of the closed quantum system? And then the closed quantum system, yeah, so at the end of the last lecture, I also gave you extreme example of the open system. So for example, if Alice and Bob are separated and then Alice is on the Earth and then Bob is on the moon. So, and then in principle, their total quantum state can be still entangled between Alice and Bob. And then if we can still consider the quantum state owned by Alice and then quantum state owned by Bob simultaneously, then we will call such kind of situation as a closed system, because we can consider every details of the quantum system. However, if there is limited communication or no communication at all, so Alice cannot tell what is happening on the moon, but still she needs to describe her own quantum state. In this case, Alice's system is called as an open system, and then what is happening on the moon is so-called as the environment. Of course, if you hear the concept of the environment, then environment is something which is surrounding you. But the reason we call such kind of entangled particle as an environment is because whether it is just next to Alice or it is far away from Alice, the problem is what happens with the Bob actually affects the quantum state of the Alice. So environment means that something which will affect your intrinsic system, but the problem is you have no control about the environment. So such kind of part is called as environment. So yeah, again, yeah, one good extreme but very easy to understand example is someone on the moon, but that person or that particle is entangled with your own particle. Yes, so, and then in that case, the second postulate actually does not tell us how we can calculate. However, if we are clever enough, then we can still, and then extreme, so if you have some particle which is entangled with environment, and that environment cannot be controlled or measured by yourself, and then in that case, you still have a way to define your or imagine about your own system, and then that's that is density matrix formalism. So we already, so as I mentioned, I already gave you an example of two particles entangled, and then we can, so something like this one, but they are far away, and then in principle, Alice cannot know what is happening with the Bob, and then Bob also cannot know what happens with the Alice, and then sometimes Alice might measure, or in the in opposite case, Alice might not do anything. But the problem with Bob is until Bob actually receives any kind of communication from Alice, Bob actually cannot tell what is happening with Alice. So, and then so in some case, Alice measures 0, and then in that case, we definitely know that Bob will be in the 1 state. However, until Bob actually measures this one, or until Alice tells what happens, Bob actually cannot tell whether his qubit will be 1 state, because in principle, this entangled state means that the state can be either 1 or 0. Similarly, if Alice measures 1, Bob will be in the 0 state, but until Bob knows that what happens with the Alice, he cannot tell. So under this kind of situation, what Bob can imagine is that, well, Alice have a 50% of chance of measuring 0, and then 50% of chance to measure 1. Because Bob and Alice knows that they are in this kind of entangled state. Then what he can do is, because he knows this kind of probability with the 0 and the half probability with the 1, so he just write down this kind of expression, and then this kind of expression is called as a density matrix. And then you might think that this is it has no no reason why we should write in this way, but you will as you learn about the density matrix, then you will realize that this is very nice or very elegant method to describe such kind of situation. Sorry. Okay, so so the first question I raised in the last lecture was, what happens if Alice measures this qubit, but she started to measure it not in the 0 or 1 basis, which is called as a computational basis, but she decided to measure along plus minus basis. Well, then the problem is, even if she measures either plus state or minus state, then the Bob will be in the minus or plus state. And then the problem is, how can Bob know what kind of measurement basis she will use? And then you might feel that, well, that's not that's a little bit complicated situation. So we cannot do anything. However, even if you just assume that Alice started to measure her qubit in the plus and minus spaces, and then Bob start to and then Bob have have plus state with the 50% of chance, and then minus state with the 50% of chance, then if you just expand the entire expression, then you are actually, I showed you that you will be eventually end up with this kind of expression, which is exactly the same with this one. So from this point, you can appreciate that this kind of formula is not some arbitrary, but it is well planned expression. And then so we will go into further about the properties of the density matrix. So let's formally define the density matrix. So first of all, we are going to consider this kind of example. So you have 90% of probability or 90% of chance to have 0 state, or only 10% of chance to have plus state. And once you see this, you might feel a little bit uncomfortable, in the sense that we are talking about the mixed basis, like a 0 state and then plus state. So you might say that, wait, shouldn't we at least consider all 0 and 1 cases, or plus and minus cases? But it is not true. When we are discussing about the density matrix, we don't have to use only the orthogonal state. So here, I just use the 2 state, but you might also have something like different amount, something like 45% of 0 state, and another 45% of one state, and then the another 10% of the plus state. And then yeah, you might still have even more different combination. So yeah, when we are talking about the density matrix or this kind of probability to have some kind of state, then we don't need to limit ourselves to the orthogonal state. And then in this case, when we are discussing about this situation, we call each of these cat vector. Yeah, so yeah, up to now we only call each of these as a cat vector, and then we say that each of these cat vector in the Hilbert space, we call them as a pure state. Then the problem here is we have the mixture of the pure state with some kind of probability. So in general, if we know that some quantum state, it will be in one of these pure state, and then each of the pure state has the different some kind of probability related to that, then we call it as a ensemble of pure state. And then it is kind of combination of the probability and the corresponding pure state. So 45% with the 0, another 45% with the 1, and then another 10% with the plus state, and then it will form a kind of set. So we call the set of the different combination of the pure state as the ensemble. And then once we are given such kind of ensemble of a pure state, then the density operator is formally defined as this way. So we already discussed this one. So how can we, let's also try to calculate the density matrix corresponding to this example. So again, the calculation is quite straightforward. So all we have to do is multiply the 90% of probability to 0, 0, yeah, which is the cat product or outer product of the same pure state, and also another 10% multiplied to the cat bra of the plus state. And then yeah, we know that this state can be expanded in this way. So if we just expand the entire term here, then it will be the combination of 0, 0, 0, 1, 1, 0, 1, 1 kind of combination. And then because we also have 0, 0 here, so if you just add them together, then the matrix, the density operator will appear, can be also appear in the form of the matrix like this one. So because now we are going to deal with the density matrix, we should also consider how does the how can we describe the change of the density matrix or the properties of the density matrix according to the postulates of the quantum mechanics. So we are going to reformulate all the postulates in terms of the density matrix. So the first postulate we are going to consider is the second postulate, which describes how does given quantum state will evolve. And then we will continue to use the same example, which we already described in the previous page. So 90% of 0 and then 10% of plus state. In this case, the second postulate doesn't tell us how does this entire situation will evolve. However, it actually tells us how does each of the case, 0 case will evolve, and how does the plus case will evolve. And then we know that in the second postulate, it says that the evolution of each of these pure state will follow this unitary operation. And then it corresponds to just multiplying the unitary operator on the this pure state or this cat vector. Similarly, if we start with the plus state, then the final state corresponding to this initial state will have only this kind of shape. So, and then the fact that this 0 goes to this state, and then the plus state goes to this u multiplied onto the plus cat factor doesn't change, does not change the probability of this situation and this situation. So it turns out that the probability, so at the end of the evolution, the probability that we will have this state will still have the 90%, while the probability to have this final state will have only 10%. So we can easily rewrite the final state in this way. So we are still using the original probability, and then all we have to do is replace the original 0, 0 with the u multiplied on 0 cat, and then bra 0 bra multiply on the Hermitian conjugate of the unitary operator, and then similarly for this case. So now what we can do is we can generalize this kind of situation. So we are going to consider some more generalized initial state with the psi I, which is the pure state with some given probability p sub I. Then we know that this initial state will evolve to the u times u multiplied onto the psi sub I, and then the probability to have this kind of final state won't be changed compared to the original probability. So if we write down the initial state density matrix of the initial state in this way, which is the simple definition of the density matrix, then we know that each of these pure state will evolve by following this formula or this expression, and then we know that because the probability won't be changed, so the final state should be still the density matrix of the final state will still follow this expression. And then in this case, we know that the unitary matrix or unitary operator and this operator are linear. So in principle, we can and then all of these operator are applied to all the terms. So they can be factored out like this one, and then which is very obvious. And then we used to have this probability multiplied on this on each of these outer product, and then that means that the summation can be actually going to this side. And then what is this one? This is the row unit. So we can say that the density matrix corresponding to the final state can be easily obtained by just multiplying the unitary operator on the left side of the initial density matrix of the initial state, and then also the multiplying the Hermitian conjugate of the unitary operator on the right-hand side. Then we can obtain the final state, the density matrix of the final state. So yeah, this is quite a simple relation between the initial density matrix of the initial state and then the density matrix of the final state. Now let's consider about the third postulate. So the third postulate was about the measurement, and then the third postulate actually provide two types of information. First is the probability to measure some value, and then another information is what will be the final state after the measurement. So let's first see the probability part. So the problem is now we have this kind of mixed situation, like 90% of the 0 and 10% of the plus state, which we already talked about before. So in this case, what we want to do is measure either 0 or 1. And then the question is, what is the probability of measuring 0 value? Well, so yeah, similar to our discussion about the second postulate, what we can do is individually consider the case for 0 and then case for plus. So if we just consider that, instead of considering that 0 has only 90% of chance, just assume that 0 has 100% of chance. Or assume that we are given 0 state, and then here I'm using the notation of the conditional probability, because we are assuming that here we are only assuming that assume that 0 state is already given, and then what is the probability to measure 0? And then in that case, we know that from our previous discussion about the measurement theory, we will have these measurement operators, and then to calculate the probability to measure the 0 value, then what we have to do is this kind of multiply the given initial state 0 and 0, and then sandwich them. We will do the sandwich. We will put the this measurement operator, and then calculate the multiply the Hermitian conjugate of the measurement operator, and then calculate multiply the quantum state from left and right, and then if you just calculate, then it should be the value should be 1, which means 100%. Yeah, and then that makes sense because we are given we simply assume that we start with the zero state, then the probability to measure 0 is 100%, of course. And then what about next? We are going to consider the plus state. So here again, we simply assume that we started with the plus state, and then the question is, what is the probability to measure 0 value? And then similar to this argument, and then we know that to calculate the probability, we should use this relation. And then if you just calculate, then you will have the 0.5%. So now the question is, what is the total probability of measuring 0? Is that 1, or is that 50 only 50%? Well, we should multiply the weight of each of these different situations, and then the total probability is that we have the 90% of chance of measuring 0 with the 100% of probability, while for this case, this one has only 50% of probability, but this plus state have a chance to have only probability to appear 10%. So we have to also multiply the weighting factor of only 10% in front of this probability. So the total probability should be calculated in this way. So this is a simple idea, but now what we can do is generalize this situation. So assume that we are similar to our previous discussion. Let's first assume that so even though our given state can be in different one of the many different pure state, let's assume that our initial state is only this pure state, and then we know that the probability to measure the value m can be obtained by this formula. And then in this case, because we already assumed that the initial state was only one of the pure state, which I describe here as put size of I. So this is a conditional probability that we have the initial state of I, and then we are trying to calculate the probability to measure m value. And then this is a formula which we are already familiar with. And then I also will claim that this formula can be turned into the trace. And then this kind of relation can be easily proven if you consider this relation. So let's say that you want to calculate the inner product between beta bra and then alpha cat. And then in this case, if you remember about the completeness relation, then what completeness relation says is that the summation of all these projection operator corresponds to identity operator. So yeah, it is this equation and this expression and these expressions are the same because this part is simply the identity. However, once we apply these things, then the multiplication or the combination of this one and then combination of these, yeah, they becomes just the scalar value. So yeah, each of these are the inner product. So they are the scalar value, which means that their order can be easily swapped. So here, yeah, I intentionally I already swapped the inner product, the order of the inner product because yeah, they are scalar value. But once we do that, then something magical thing happens because now you can see that this has expression for the trace. So what does a trace? The function of the trace is multiplying the same basis factor from left and the right, and then just the sum of all of them. That is the definition of the trace. So we can, yeah, in other words, we can just rewrite the inner product expression by switching their order. Yeah, so if you have the inner product between the bra and cat, all you have to do is make a outer product composed of the cat and bra, and then yeah, just to put the trace. So that's how you can prove that this equation, this equality is valid. So once we have this discussion, this value only corresponds to one of these p conditional 0, 0 or p conditional 0 plus. But what we are interested is the total probability. And then to calculate the total probability, we should follow the same rule. So the total probability to measure value m should be calculated by multiplying the weight on each of these conditional probability. And then now, once now we have this expression for p of mi. So yeah, if I replace them, and then we know that each of these probability can be, and then we know that the trace operation is a linear operation. So what we can do is multiply, just to move this piece of I into the parenthesis here. And then moreover, because this is a linear operator, so even the summation can be moved into inside here. And then so if you just move this one and then move this summation, then this part will become exactly like the definition of the definition of the density matrix of the initial state. So what I can do is replace this part with the just the density matrix. And yeah, let's consider, let's try to calculate this total probability based on this derived formula. So we know that in the previous example, when we are given this kind of mixes, this kind of mixed pure state, and then the density matrix will be can be obtained in this way, which was already shown in the previous page. And then if I just try to calculate the probability to measure a zero value, then all I have to do is plug in the measurement operator for zero in here. So and then we know that the zero measurement operator corresponding to zero can be is this one. So it can be also represented in terms of the matrix. And then for this simple matrix, we know that the Hermitian conjugate of this one will be the same, same shape. And then if you just multiply those two matrix, then yeah, the multiplication of those matrix will just appear as this one. So I have this part, so this part corresponds to here, and then row comes from here. So if you just multiply this matrix on here, then you will only left with this term because all the other terms are 0. So you will have only this part, and then the trace also corresponds to the summation of all the diagonal terms. So yeah, if you just have only this term non-zero, then this will be just the total probability. And then this is already obtained here. So we can confirm that this kind of formula is a generalized form of calculating the total probability. In the previous page, what we discussed was only the probability. But now what we have to consider about the quantum state after the measurement. So in the previous page, what we calculated was the total probability to measure the M if we are given some density matrix, or we also calculated the conditional probability to measure value of M when we our initial state was precise of I. Yeah, so these are the two formula. But when we are considering about the resulting quantum state after measuring some value of M, then yeah, we also have to consider different pure state. So let's first consider the pure state. Yeah, so we know that our given quantum state might have different precise of I. Yeah, so precise of 1, precise of 2, precise of 3 with different probability of p sub 1, 2, 3. And then here we are only considering about the precise of I case, and then assume that we measure the M. Now the problem is, what we have to do is consider the probability, not the probability, but you know, if we just assume that our final measurement result is M, then we have to consider what will be the final total final state. But before we consider that, yeah, let's separate the different pure states, and then if we have this precise of I state, if we started with this precise of I state, then according to the new formulation of the measurement theory, then the corresponding quantum state will be described in this way. So it is just a same formula which we derived in the last lecture. But now we have to consider about the probability of having this one. So what is the probability to have this one? Is that P of M? Of course not, because we are only considering about this one. So is that corresponding to this conditional probability? You might feel maybe, but it is not actually true. Here, what we assumed was, we assumed that our initial state was the precise of I, and then we calculated the probability to measure M. However, here, what we are trying to calculate is the probability of having psi I when we already measure the result M. So here the probability can be different, and well, yeah, so we might have different yeah, so this kind of probability formula considers different value of M. However, here we are only considering the case when we measure a value of M. So here the condition, the assumption is we measure the value M, and then we are now asking what is the probability that the result of measurement M came from this psi sub I. So that is a little bit tricky, but these two probabilities are different. And then I didn't calculate. I didn't show how to calculate this value yet. And then there is a very simple relation. And then just assume that we can calculate this probability, this conditional probability, and then what we can say is the density matrix of the final state can be expressed as in this way, and then in this case, we have even if we measure the same value like m, the resulting quantum state might be a little bit different, or it might depend on the initial state, like psi sub I. So what we have to do is add each of them individually, and then we also have to multiply the probability to have this event. And then here I'm just keeping it here. And then if I replace this formula with this, then it will appear like this one. And now what we can do is try to calculate this probability. And according to the elementary probability theory, or what is called as the Bayes theorem, then this conditional probability can be obtained by calculating the probability to have both m and I, and then it will be divided by probability of m. And moreover, according to the Bayes theory, Bayes theorem, this probability, the probability of having both m and I, can be obtained by this multiplication of p sub I, and then the conditional probability of this one, and then the denominator is the same. So if we replace this with this expression, and then according to our previous result, P of m with I is simply like this one. So I can just replace this expression, this one, with this expression, and I have this P sub I here, and then P of m is actually obtained here. So the denominator will be replaced by this one. So these parts are just representing this part, and then I just copy down the remaining part like here. And now you can see that the numerator and then denominator has the same factor. So they will just cancel with each other. And then the denominator will have only this part. And then I have this factor. So it will come out here. And then the entire expression will look like this one. And now what you can see is these are again the linear operator m sub m, and so then now we can move this p sub I into between these two operator, and then even the summation can go between these two operator. So if you move these between here, and then everything inside here can be replaced by simply the density matrix. So so this is the formula for the measurement after we measure the resulting m. So even if even when our initial state is given in terms of the density matrix, then you can immediately calculate the resulting density matrix of the resulting state. So up to now, according to all the discussion, you might have an impression that the density matrix is can be used only when you have the mixed state of the pure states. So and then you might think that if you are given some pure state, where your state is psi cat vector, then you cannot use the you might have the impression that you cannot use the density matrix, but that's not true. If you have just this pure state, then only one pure state, then all you have to do is just write down the density matrix as the outer product of the same same vector. So density matrix can both describe the pure state and then the mixed state. And then in this case, if you are, let's say that you are given some density matrix, and if you can factor out in such a way that the density matrix eventually can be written as the outer product of the same vector, then you can say that it is a pure state, while if it cannot be factored out in this way, then it is called as a mixed state. And then sometimes it is also called as a mixture of the different pure states in the ensemble. And then how can you determine, how can you quickly determine whether some given density matrix represent the pure state or a mixed state? And then there is a very simple formula. So if you just square the given density matrix and then calculate the trace, and then if you have only the pure state, then trace of this square of the density matrix will always become 1, while if you have a mixed state, it cannot become 1. So it is less than 1, and then that's the quick way to confirm that. So I will, the proof of this one is quite straightforward. So I will leave it as a homework for to prove this one. And then and moreover, we can also consider even more extreme case. So let's say that you have two density matrix. So the first density matrix is composed of the 50% of 0 and 50% of 1. And you have another density matrix representing the 30% of plus state and 70% of the minus state. And now the question is, what happens if you have a probability of having row 1 with the 25% of probability, while for the rest of the 75% of probability, you will have row 2. Then, can you describe the final can you describe the resulting state of resulting quantum state corresponding to this situation? And of course it can be. And then the formula for this one is quite straightforward. All you have to do is multiply the probability of 25% to rows of 1 and then 75% to rows of 2. So that's the formula. And then the proof of this one is also straightforward. So what we can consider is that this situation can be also considered as zero state will appear with the with the total probability of product of the 25% multiplied by 50%. So overall the zero state will happen with the probability of the 1/8, something like this. And then one state will also appear with the 1/8 probability. And then for this one, you can also multiply to calculate the probability having this one, then it will be 4 times 3, 3/4, 4 multiplied by 10/3. So it will be 40, 9/40, 9/40 probability. And similarly, you can also calculate the probability to obtain this one. Yes, and then it will be like 21, right? Sorry, yeah, it cannot be correct. Well, yeah, you can. Sorry, yeah, it is correct. Yeah, so yeah. So yeah, eventually you can obtain this kind of probability, and then you can either consider you can actually consider multiplying this probability to 0, 0, and then multiplying this probability with the 1, 1, and then multiplying this probability with plus, plus, and then similarly for this one. Yeah, so if you just consider such kind of situation, then what you are actually doing is multiplying this probability to each of these. So here, yeah, I just represented this probability with the piece of ij, and then I represent this part, and then the j represent each of these. So yeah, you will have this kind of probability, and then what you will end up doing is summing up all the possibility like here, and then that one actually corresponds to calculating the individual density matrix for this case, and then another density matrix for this case, and then all of them will be multiplied by the overall probability, like 25% and 75%. So eventually, the result, the total density matrix of the total situation can be expressed in this way. So that's how you can combine the mixture of the mixed state. Yeah, I know it is a little bit confusing, but this is yeah, quite interesting idea.